We are commencing with today's lesson, and good to have you guys back. And I can see Eunice has also joined us. Good morning, Eunice.
Good morning, sir.
How are you?
I'm fine. How are you?
I'm doing fine as well. So awesome. Um, Today we are dealing with the topic of linear momentum and collision. So I do realize that especially some of you guys who are following the lessons that I give for the whole PCM NS students, I'm sure you will agree with me that we did even tackle the topic of momentum and collision with everyone in the NS PCM group. Okay, so and I'm sure you guys have studied it, and you guys, even the test that I gave you, it was having some question on momentum and collision. So but what we are doing, especially for these extra lessons, is that since we started all the way from vectors, again, we went back to vectors. We want to make sure that we polish up on these topics. Even if you have read about them, you have learned them, and you seem almost as if you have really understood and grasped the topic, but there are still some of those hanging elements that we need to filter out and that we need to actually clear out so that you guys become expert in all the topics in physics 1010. All right. So today we are looking at linear momentum. I'm sure most of you guys are familiar with this topic. So, but I'll take it slow to make sure that the biggest and grindiest concepts under these topics are well elaborated, and you guys get to appreciate this topic and just get to understand it to the core. So, okay. So let's delve into the lesson. So we are saying that momentum, especially in physics, we usually just describe it as the product of mass and velocity. All right. The product of mass and velocity, but you realize that in vocabulary, in literature, and in just speaking in English vocabulary, you discover that momentum is used in many different ways. All right. Momentum can be used to describe just that pressure, that force, that drive. You know, if someone has a lot of momentum, they have that drive with them, that force to push through. So, but in physics, we just say that momentum is just a product of mass and velocity. So, and the simplest formula for momentum is just this symbol is a Greek symbol, and it's called rho. This is not P. So even when you are writing your equations, momentum, make sure you indicate it as rho. This is not P, this is rho. Okay, so rho mv. So momentum is just simply mass times velocity. All right, so two objects can have the same velocity but not the same momentum, and two objects can have the same mass and not the same momentum. So to have the same momentum, you have to have the same combination or the same product of mass times velocity. All right. So again, we are saying that momentum is a vector, and in a 2D plane, it can have components in the x-axis and in the y-axis. All right, as we'll see when we delve deeper into the topic. So we are saying momentum, we can have momentum of an object in the x-axis and momentum in the object in the y-axis. So what makes it so is because velocity is a vector. So velocity can have a component in the x and component in the y, therefore giving momentum also a component in the x and the component in the y. At the end of the day, the magnitude of momentum has to be the component of it in the x-axis squared and the component of it in the y-axis squared. So that will give us the magnitude of momentum. And of course, since we are dealing with an object, we can always manage to factor out the m and have our momentum given as the velocity component in the x-axis squared, the velocity component in the y-axis squared, and then we can even determine the angle at which that momentum is directed by just getting the y component over the x component, the arctan or the tan inverse of component in the y-axis and component in the x-axis. So this is basically just an introduction of momentum, some of the things that we already know. But one of the things that I've realized is that you guys are good with solving a pen and a paper, especially if you have come across that question before. It's very easy. You guys just go solving, you just multiply, add, do what. But when it comes to multiple choice questions, you don't do well. Even as I've been marking the test, I've discovered that multiple choice questions, most of you are not doing well. Why is that? It is because you guys don't understand this concept to the core. All right. So whenever they twist the language here and there, you fail to relate, you fail to see the right answer because you guys know the mathematics, you know how to solve, but you don't know the concept. So the idea of even going through this topic again is so that you really get to appreciate the concept to the core and make sure that you understand everything to do with momentum and the like. So let's continue. And when we talk about conservation of momentum, so when a collision occurs in an isolated system, all right, first of all, the system has to be isolated. There have to be no external forces or interferences tampering with the system. So when a collision occurs in an isolated system, the total momentum of the system doesn't change with the passage of time. All right. So when momentum happens, momentum does not change. So what we have in the initial stage, momentum initial should be equal to momentum final. When a collision happens in an isolated system, we have to make sure that we conserve momentum. So initial momentum has to be equal to final momentum. All right. And this is not just for an object, this is for a system. So there may be two masses or three masses or four masses interacting, but what we need to make sure that is the case, or the principal thing is that momentum initial has to be equal to momentum final. This is your basis for momentum. Momentum has to be conserved. So let's take, for instance, two objects collide in an isolated space. The following equation describe how momentum is conserved in a straight line as well as in 2D. All right, so let's see how we can conserve momentum if something is happening in a straight line, all right, head-on collision. And also, we also have to look at a situation where momentum is conserved in 2D. All right. So here, in fact, what I've highlighted here is a case where we have two masses. We have mass 1 and mass 2. All right. So now what I've even shown here is that it's a special case of how to manipulate momentum equation. You can actually get to say change in momentum of one mass when it collides, because what we have here on the left side is just change in momentum of mass 1. When it collides with mass 2, change in momentum of mass 1 has to be equal to the change in momentum of mass 2. So on the left-hand side, I have mass 1 times velocity 1 final minus the same mass 1 times velocity 1 initial. So the final momentum of mass 1 minus the initial momentum of mass 1 has to equal the final momentum of mass 2 minus the initial momentum of mass 1 or of the same mass 2. So what I've shown here is just another way of how we manipulate these equations of momentum, of showing that the change in momentum, if we have two masses colliding, has to be equal, the change in momentum of one mass has to be equal to the change in momentum of another mass. Now we are putting a minus here because usually when momentum takes place, all right, you will see when you manipulate these equations, you find that change in momentum of one mass will be equal to the negative change in momentum of the other mass. All right. So now this concept that we're trying to establish here is just simply the concept of conservation of momentum, that momentum at the end of the day has to be conserved, and we'll be able to see it clearly when we look at some examples. But at the end of the day, in one dimension or in a straight line, like I've said, in a straight line, you will discover that if you have two masses colliding, momentum has to be conserved. All right, are we following, friends?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Awesome. Precious, you are late.
Yes, busy.
Okay. Understood. So
I've got a question.
you have a question, Chipo?
Yes. On the first statement, where you explained that two objects, when they collide, they have to be isolated, meaning there is no external force acting against them, right?
Yes. Yeah.
I think I explained for me the collision from, for example, I say A is B not an external force acting on.
Okay. Now, when we talk about external forces, in fact, the next slide will be able to answer your question properly. All right. So, for example, you are running. Probably you are looking behind, but you are running, and then you don't know that Mr. Gilbert is in your way. All right. You are running, but then you discover you are running with a certain velocity. Immediately afterwards, or in just a moment after, you bump into Mr. Gilbert. All right. If Mr. Gilbert is not leaning against a wall, or he's not leaning against a tree, he's isolated, he's just standing free in space like that. If you hit him, the momentum that you had, all right, in the initial stage should be equal to the momentum that you will result after even you have had that collision, because there is no external force. There's no one trying to hold Mr. Gilbert or hold you back. That is what is meant by isolated system, is when one object bumps into another object which is free to move. But if that object, for example, if Mr. Gilbert is leaning against the wall, if you bump him into him, he's not in an isolated system because he is already being shielded by the wall, such that you cannot clearly determine what will happen after, since he is leaning against the wall. But if he's free in space like that, if you bump into him, you will deliver your momentum. In fact, when you bump into him, momentum will be conserved. But what you are talking about when an external force comes in, that is what is called impulse. So we'll look at the case of impulse just in the next slide, where we'll talk about when an external force comes in.
Okay, thank you.
Is that okay? Chipo, are you still there?
Yes.
Are you okay with it?
Thank you. Yes, I am.
Okay, good. Awesome. So it has to be in an isolated space, no external force. But then, actually, before we even come to the idea of impulse, let me also talk about the idea of two-dimension. Now we have looked at a situation where it is just in a straight line, but what about in a case where it is in a two-dimensional space? So in a two-dimensional space, we see that for the diagram shown below, momentum has to be conserved, all right? If momentum has to be conserved, meaning in the x-axis, momentum has to be conserved. In the y-axis, momentum has to be conserved, all right? So momentum of mass 1 in the x-axis, initial, plus m2 v2, meaning momentum of mass 2 in the x-axis, initial, has to equal momentum of mass 1 in the x-axis, final, plus the momentum of mass 2 in the x-axis, final. So this is just telling us that in the x-axis, we have to make sure momentum is conserved. When we apply the equation of momentum in the x-axis, we must make sure that it is conserved. And also when we apply the equation of momentum in the y-axis, we have to also make sure that it is conserved, all right? So this type of collision is called glancing. So sometimes you may hear the word glancing collision in a test or in an assignment or in any quiz, glancing collision. So this is where, for example, one object is at rest and another object comes and collides with it. So you'll find that if it just glances this other object at rest, these two bodies will deflect in a 2D plane. They'll deflect in a 2D plane, and the equations of momentum have to be conserved by resolving the component of it in the x-axis and resolving the component of the momentum in the y-axis. So usually one of the most common instances that you will find with is, for example, if mass 1 is moving and mass 2 is at rest, you find that mass 1 in the x-axis, it is moving with a certain momentum. Mass 2, if mass 2, for example, is at rest, what will happen after the collision in the x-axis is that you have to resolve the component of mass 1 or the component of momentum 1 final in the x-axis. So you will find that if this is mass 1, after the collision, this mass 1 will deflect at an angle. So you have to resolve the component of this momentum of this body in the x-axis. That is why we are putting cos theta to the velocity of mass 1. Find the velocity of mass 1, we are adding cos theta to resolve the component of this momentum in the x-axis. And also for mass 2 as well, you discover that it also goes at an angle. So since it has gone at an angle, you have to make sure that you resolve the component of that velocity in the x-axis to get the momentum in the x-axis. All right, and then you discover that in such a case, you find that momentum in the y-axis is not there because both of these objects, this one is at rest, this one is moving in the x-axis. Initially you discover that in the first instance, they don't have momentum in the y-axis. But then after the collision, because after the collision, the two balls move at an angle, you discover that mass 1, also you need to find its momentum in the y-axis. And then the reason why sometimes you may find that in some equations they have put the negative sign there is to show that this other mass, certainly it will go towards the negative y-axis. It will go in the negative direction. This one will go in the positive x-axis, y-axis. This one will go along the direction of, or in the direction of the y-axis. No wonder when we are doing conservation of momentum in the y-axis, mass 2 has been given a negative in advance. But even if you put a positive, you are still fine as long as you take note of this angle. All right. If you get this angle, which is just given here as phi, then if you just get it directly, then you must make sure that you put a negative. But if you calculate it with respect to the x-axis and you move all the way, if the angle, when you are determining it, you move like that. If that is your angle. If your angle, you determine it with respect to the x-axis and you move counterclockwise like that, then it's okay, you can put a positive here. But if you get the angle just the way it is there, below the x-axis, then you must make sure you put a negative. So the reason why they have put a negative is because they have gotten the negative angle, because they have gotten it below the x-axis. So pay attention and make sure that you don't make a mistake of confusing yourself with the positive and the negative, so that at the end of the day you even get a wrong answer. Make sure you are careful. Are we following, friends?
Yes, sir.
Yes, sir.
Have we gotten why they had put a negative here?
Yes, sir.
Yes.
Okay. So always pay attention to the angle given.
Sorry, sir, for taking you back. Can you repeat on the negative?
Okay. So I'm saying that the reason why we have put a negative in when resolving the component of momentum in the y-axis, of course, at first instance, we see that when an object is moving and then it collides with another object, if this object is moving the x-axis and this other object is at rest, we expect both of these two bodies to have zero momentum in the y-axis because they are not moving the y-axis. But after collision, mass 1 goes towards the positive y-axis, but mass 2 goes towards the negative y-axis. And this is usually the case almost all the time when a glancing collision happens. One object will go towards the positive y-axis, another object will go towards the positive another object to go towards the negative y-axis. It is almost always the case. So since we know that this mass 2 goes towards the negative y-axis, we usually sometimes put the angle to be, we usually add the negative. We put a negative to mass 2, to the momentum of mass 2, to show that indeed it has gone towards the negative y-axis. But that is only because the angle that we use is below the positive x-axis. We take it below the positive x-axis. But if we move counterclockwise like that, all right, and take this other outer angle like that, then here we can put a positive. If we took the angle to be from the positive x-axis, go all the way until we meet this point, then we are supposed to put a positive there. All right. Are you clear now?
Yes.
Okay.
Yes, that's
Sir, I have a question on the velocity.
Yes.
There's a question that comes multiple choice where it asks whether the velocity is the same after and before collision. What could be the answer?
The question is saying what?
Will the velocity be the same for the object after and before collision?
Usually, when a collision happens, velocity is not usually maintained. All right. So if an object was moving at 5 meters per second after collision, it must change. It can't be the same. It can only be the same.
Does it decrease?
Sorry?
Does it decrease or increase after collision?
So it depends. All right. If you are running at 2 meters per second, all right, and then me, I come behind you, running at 5 meters per second, and I bump into you. If I bump into you in the direction towards where you are going, if I come behind you and bump into you, you are going forward, running at 2 meters per second, and then I bump into you from behind, your velocity will increase. But if I bump to you in front, I hit you, you find that your velocity will decrease. All right. So it depends. It's not always. I'm sure you should check if it was a multiple choice question, then you should check the other option. The other option maybe could have been better, but don't put the option which says it will remain the same or it will increase. It all depends on what the nature of that collision is.
Okay.
Is that okay?
Yes.
Okay. So we have looked at momentum, and it's good that you guys are asking questions so that you get to clear your
Sorry.
mind. There's another question?
About the same that Chipo is from asking. So it means the answer can be, it's not always the same.
Yes, if it is there on the options, it will not, the velocity will not be the same. The velocity will change. Yeah.
Okay.
Awesome. Yeah.
And sir, when getting the angle in the x-axis, you just get it the way it is. There's no need of putting negative. How is it? It's for the y-axis. Then you're saying that you put the signs according to the way you got in the angle.
Okay. So in the x-axis, for example, if you have been given that this body deflect, for example, this one is at maybe 30 degrees, it deflect, and this angle is 30 degrees, and this other angle which is down here they say maybe it's 50 degrees. All right. So if they give you like that in the x-axis, just place it like that. Here you put the 30 degrees, here you put maybe 50 degrees. But in the y-axis, if you take this angle for mass 2, for example, if it was given as 50 degrees, if you take it just like that, 50 degrees, then you make sure you put a negative there because it's a negative angle. Because sine is an odd function. So you must make sure that you put a negative there. Have you guys learned about even and odd functions in math?
Yes.
So you know that sine is an odd function. So the sine of a negative angle is negative. No wonder we put the negative in advance, because the sine of a negative angle, this angle, if it is taken like that, it will be negative. So the sine of a negative angle, we put the negative in advance so that we don't need to put another negative there. But cos of a negative angle, we are using the same angle here. Cos of a negative angle is positive. No wonder here we put a plus, because cos of a negative angle is positive, but sine of a negative angle is negative. No wonder we put a negative in advance. But if you don't want to put a negative, then get the angle starting from the positive x-axis all the way until you meet the object, like that. Is that okay?
Yes.
So we continue on. Yes.
So there, if you get it from the positive, so it means that you're going to subtract the angle, for example, the 50 that you're from mentioning, meaning you subtract it from 360.
Yes, yes.
Okay.
Is that okay?
Yes.
Okay. So, we have looked at momentum, and I'm just explaining some of these theories so that you guys get to appreciate the concept properly. So now, another part that I would also want to talk about is what type of collision, if a collision happens, is it elastic or inelastic, or is it perfect elastic? Is it perfectly inelastic? So if the collision is elastic, so these are some of the questions, sometimes they come even in the multiple choices, that is, or even, I'm sure even in the test you saw a question saying, is the collision elastic or not? So if the collision is elastic, both momentum and kinetic energy is conserved. So momentum is conserved and kinetic energy is conserved. Therefore, the following equation applies. This equation is the equation for kinetic energy. All right. So for example, this object is the one that was moving, which was having some kinetic energy. This other object was at rest. So this other object will not have any kinetic energy. But even after collision, if momentum has to be conserved, if kinetic energy has to be conserved after collision, the kinetic energy of this object and the kinetic energy of this object will have to be related like this. So this is kinetic energy of this object which is moving. They have not shown the kinetic energy of the other object because it was at rest. So you have kinetic energy of mass 1 in the initial stage has to be equal to kinetic energy of mass 1 and kinetic energy of mass 2 in the final stage. So this is before collision and this is after collision. That is how we make sure that the collision is elastic. We have to make sure that we conserve kinetic energy. Are we clear on that one, on the explanation of elastic collision?
Yes, sir. May you kindly repeat?
Sorry?
Repeat.
Or I repeat, okay? What I'm saying is that collision, for collision to be called elastic collision, this word here, elastic collision, both momentum is, we use these equations to conserve momentum in the x and momentum in the y. And kinetic energy should be conserved. So we also must make sure that kinetic energy that we have here is equal to the kinetic energy that we have there. All right? So therefore, this equation tells us that kinetic energy, this is initial, has to be equal to kinetic energy final. All right, we see that, for example, in this case, only this object had kinetic energy, but this other object did not have kinetic